Hello student, my name is Kalal from Alja Institute of Engineering and Technology. Welcome to my online lecture series of refrigeration and air conditioning subject. Today I will discuss VCRS cycle, or in this chapter discuss topic is a refrigerant vapor compression refrigeration system and factor affecting COP of vapor compression refrigeration system. In short, vapor compression refrigeration system we denoted by the just VCRS cycle. Okay, let's start. Different vapor compression refrigeration system or different process. First, case number 1, cycle with dry saturated vapor after compression. First, what is the VCRS cycle? Just keep in mind, VCRS cycle is like this is our condenser, this is our compressor, and this is our evaporator, and this is our expansion valve connected. So here refrigerant flow from point 1 to point 2, and this is point number 3, and this is point number 4. 1 to 2 is a compression, isentropic compression. 2 to 3 is a condenser at constant pressure, and 3 to 4 is an expansion process, and 4 to 1 is an evaporating process, or our desired effect 4 to 1. Just keep in mind. Okay, so different types of cases. How to differentiate this one? It depends on the inlet condition. Point 1, this will enter inside the compressor. According to this, different cases are differentiated. First case, cycle with dry saturated vapor after compression. Okay, that means if output of the compressor is dry saturated vapor, that means its dryness fraction is 1 or above dry saturated. That means phase is in the superheated phase. Okay, so draw a diagram. Here, this is our dome, totally our dome. This is our dome, this is our pressure line, and this is our enthalpy pH chart. Point 1, if point 2 after compression, output after compression is a saturated, is a dry saturated, that means point 2 lies on this dome, or this is saturated curve line, saturated vapor curve line. Okay, so point 2 lies on this saturated vapor line. If point 2 lies on this curve, it is sure that point 1 lies in the inside. That is a weight reason. Just remember this. This is a dome. Outside dome is a superheated, and inside dome is a weight reason. And after this is saturated liquid line, and this is a liquid phase. Okay, just remember this one. So this is our pH chart for this case. Similarly, TS diagram for this one. 2 point lies on here, is on the curve, and 1 point is inside the dome. 3 point and 4 point is similar like previous lecture. Okay, so 1 and 2 is the entropy is the same. So what is the COP of this system? We already know that COP is refrigeration effect divided by work done, H1 minus H4, H2 minus H1. COP for different cases are same, but how to calculate the enthalpy for different point is a different. Okay, so point 2 lies on the saturated curve. That means this entropy or enthalpy is given in the numerical or chart, or we can say table form. So main things is that not given in the numerical, that is of enthalpy at point 1. Okay, enthalpy at point 1. Enthalpy at point 1, how to calculate? Enthalpy at point 1, already we know that enthalpy at point 1 is equals to Hg plus dryness fraction Hg minus Hf. This is the formula for calculation of enthalpy at point 1. We apply this formula at point 1. This is the entropy, and this is our enthalpy formula. At point 1, entropy, how to calculate? Because S1, SF1 plus X1 is what? Dryness fraction. Because point 1 lies inside the weight region, that's why X1 is called dryness fraction. What is HFG? This formula also we can write. S1 is equals to SF1 plus X1 SFG, SG minus SF. Okay, what is HF? 1. HF1 is the enthalpy at point at up to this, and we calculate the enthalpy up to this one. This is the enthalpy, this is HF, and this is our enthalpy for calculating. Already we know that this one HF and this one is calculated by HFG. According to this, we can calculate the enthalpy. Similarly, case 2, cycle with superheated vapor after compression. Cycle with superheated vapor after compression, that means point 2 lies outside the dome. Okay, if output of the compressor is superheated, so this is the point 2, that is a compressor outside the point 2 lies outside the dome. That means we apply S1 is equals to S2 enthalpy at point 2. How to calculate? So we know that the enthalpy up to this one, there is the Hg plus this much amount of enthalpy. This is the MC delta T. We can apply Cp of vapor T2 minus T2 dash. Okay, what is T2 dash? This is temperature. So we use this formula and we calculate the enthalpy at point 2. Similarly, for the pH chart, this is our pressure and this is our enthalpy and this is our TS diagram. So this is our some little bit curved line. Okay, 1 to 2. So and COPs remain same, but calculation of enthalpy is a change. How to calculate? First we calculate entropy at point 2. S2 equals to S2 days plus 2.3 Cp of vapor log T2 days by T2 days. If you not put 2.3 here, so it just write ln, natural log. So natural log converted into log, that is 2.3 multiplied. Okay. Now enthalpy at point 2, that is H2 is equals to H2 days plus Cp into degree of superheated. How much amount of degree is superheated? That is a MC delta. Just MC delta T you can apply. H2 days is what? H2 days is enthalpy up to this point. Enthalpy up to this point. This enthalpy amount is calculated by this one formula of this one. Next is cycle with the wet vapor before compression. Cycle with wet vapor before compression, that means point 1 condition. Point 1 is lies inside, and if point 1 is lies inside, it is sure that point 2 is already lies inside the dome. So it is a very tough to calculate, because here 1 point enthalpy and 2 point enthalpy both have to calculate, because 3 point is on the dome, 3 point is on the dome, so it is already given, but 2 and 1 point is inside the dome. That's why we use formula for the calculation of 2 and 3. If output of the compressor is wet vapor, that is known as a compression cycle with the wet vapor before compression. Output of wet vapor. Wet vapor means it is a combination of vapor and liquid mixture. It is a TS diagram for this one, and coefficient COP remains same, no changes in COP, but entropy, calculate the entropy S1 because it's inside the dome. SF it is also, we can write as F1 plus X1 SG1 minus SF1. Okay, if in table SG and SF is given, then we calculate the S1. Similarly, S2, because it is in dome, so S1, S2. Enthalpy at point 1. Already we discussed H1 and H2, enthalpy at point 2, both the formula, because inside the dome we calculate H1 and H2 by using of this formula. Now, case number 4, cycle with superheated vapor before compression. Cycle with superheated vapor before compression. That means point 1 lies outside the dome, because saturated vapor line means saturated vapor line. So it means if input of compressor is superheated, that means dryness fraction is more than 1, or we can say not more than 1, lies outside the saturated vapor line. Okay. This is the case number 4 diagram. This is 1 point entering in the compressor, lies outside the dome. This is our dome. This is our TS diagram. Okay, this is our TS diagram. Or this 1 point entering into the compressor, superheated phase. So this is our pH chart, because 1 and 2 point is lies outside the dome. That's why in pH chart is also outside the dome. Okay. So COP remains same, but calculation of H1, H4 and H2 are different from other cases. So first of all, entropy at point 1. This is the formula, entropy at point 1, because the point 1 is lies outside the dome. That's why we use the log formula. Okay, so S1 dash is nothing but Sg1 at corresponding to this point. Okay, and 2.3 CPV. Just remember CPV vapor, because point 1 is lies outside the vapor phase, superheated phase. So we use CP, specific heat rate, vapor phase. Okay. Similarly, enthalpy of vapor point, MC delta T, because point 1, and this is H1 is nothing but Hg1. Okay. Similarly, entropy at point 2, same formula of same. Similarly, now enthalpy at point 1, exactly enthalpy at point 1 we calculate like using this formula. Now case 5, cycle with undercooling or subcooling of refrigerant. If output of condenser is subcooled liquid, that means condenser is a subcooled. Here we draw a TS diagram. 3 dash is a saturated liquid line. So here temperature drop, this is subcooling phase. This is called subcooling phase 3. This is our subcooling phase. So here 3, or if subcooling is done, just remember subcooling is done, that means COP increases. COP of the system increases. This is the pH chart for this one. Okay, this is subcooling process. Okay, 3 to 3 days, 3 days to 3, and COP remains same, but calculation is different. Entropy at point 2. Point 2 is what? Here this is lies outside the dome. That's why we use the log formula for this entropy formula. Just always remember this formula if point 2 lies outside the dome. And enthalpy at point 2, H2 is equals to H2 dash, nothing but Hg at point corresponding to, because point 1 on the dome. That's why this value is already given. So H2 is lies outside the dome. So we use the formula H2. Now, enthalpy of liquid refrigerant at point 3. Why point 3? In this case, and H3 is calculated, and H3 is calculated, which is equals to H4. We know the value of H3 dash in the numerical. No. But H3 is not known. So how to calculate? H3 is equals to H3 dash plus Cp of liquid delta T, temperature difference, or degree of subcooling, or we can say degree of subcooling, undercooling or subcooling. Cp of liquid minus, sorry, here use minus because it is less than this one. Okay, so we use this formula. Just remember in mind to calculation or for numerical point of view. Now, factor affecting COP of VCRS. Which type of factors affect on the COP of VCRS cycle? Okay, first factor is the effect of suction pressure or evaporation pressure. Where is suction is done? At point here. Here is suction. The 1, 2, 3, 4. And again, this is our cycle. Okay, main cycle. 1, 2, 3, 4. And pressure is some upon, there is a suction pressure PS. This is our suction pressure PS. Okay, and now we do suction pressure is reduced. If suction pressure is reduced, and we know that the COP formula is what? H1 minus H4 divided by H2 minus H4. Okay, if suction pressure is reduced, what happened? This value 4 is shifted to downward and 1 is shifted to here. So value of H1 dash minus H4 is less compared to H1 minus H4. If value is less after reducing the pressure, suction pressure, that means COP reduces. This is our funda. Okay, pressure decreases, specific volume of vapor increases, work required increases. Work required is what? H2 minus H1. So first, if 2 to 1, this much amount of work, 2 days to 1 days, this much amount of work is also increases. Work is also increases, and COP is decreases. Similarly, if it is reverse, suction pressure is increases, so condition are reverse. Now, same effect on discharge. Discharge is pressure or condenser pressure. This is discharge or condenser pressure. If pressure is discharge pressure increases, this is our condition, discharge pressure PD, and this is our PD dash. If discharge pressure increases, what happened here? This value shifted here, 2 days shifted here, the work of compressor increases. First, compressor work increases, and 3 point here, that means H4 lies here. Before increasing discharge pressure, 4 is less here. That means work of compressor increases and refrigeration effect decreases. That's why COP of the system decreases. Okay. This is the pressure. If discharge pressure increases, work required increases, refrigeration effect decreases, hence COP decreases because the area is increases. Now, effect of evaporator and condenser temperature. If we increase evaporator temperature or condenser temperature, so condenser temperature is increases. So similarly, evaporator temperature decreases. If evaporator temperature decreases, condenser temperature increases. If evaporator temperature decreases, condenser temperature increases. By showing the diagram, the work out required increases. Why double arrow? Because more work is required. Refrigeration decreases, hence COP decreases. If evaporator temperature decreases. Clear? Next, effect of superheated vapor after evaporation. 4:1 is evaporation, standard evaporation. 4:1. This is 1, 2, 3, and 4. If evaporation, 1 point lies on the saturated vapor line. If superheated phase, that means beyond the saturated, that means 1 point is shifted here, 1 days. So that's why new compressor work is like this, and refrigeration effect increases. So let's specific volume of vapor increases, refrigeration capacity decreases. Work required increases, refrigeration effect decreases, and hence COP decreases. So like 1 and 4, this is our refrigeration effect before superheated, and if superheated done, RE increases, but RE decreases corresponding to this work is more, required work is more compared to RE. That's why COP is decreases of this system. Thank you so much.